Welcome to video 14 on the TTB course. This video is from part 4 of the course. In part 4, we consider techniques for monitoring TT systems. In this video, we consider ways in which we can check the processor software. The material in this video is based on Chapter 14 in the ERES2 book. As usual, I suggest that if you have not yet read Chapter 14, you stop the video now, read the book chapter, and come back and watch the video again. So the primary purpose of low-level power-on self-test operations that we considered in video 13 is to confirm that each processor in our platform is fully operational. In many designs, the next key test involves checking the processor software itself. There are two key issues that we need to address at this point. We must ensure that the correct processor software has been installed. We must ensure that the installed processor software is free from corruption. These are key issues, and in several projects that I have been involved with, it has been an area that's been discussed many times during the system design process, is how we will ensure the correct software is installed on the system and that it is free from corruption. This is not always a trivial process. Let's begin with the first key question. How can we tell whether the processor software has been corrupted? Logically, we need to check that the installed software is free from corruption before we can check that we're running the correct software. This is logical but presents one of the challenges. We're relying on the software to check itself, so before we can check we have the correct software, we need to check that the software is free from corruption. To support checks for software corruption, we will usually calculate a golden signature from the processor software executable code and load this into memory, typically flash memory, along with the executable code itself. So what will typically happen is we will calculate at design time, we'll calculate the golden signature, we will load that into memory after the executable code. We can then have the system recalculate the signature at runtime and compare the result with the stored value. If there are discrepancies, we will try to shut the system down. In most cases, a golden signature is essentially a CRC. And it will usually be added to the end of the executable code before this code is loaded into the processor. So we're going to calculate the golden signature from all of the processor software that's included on a particular processor. Hertel, and you'll find a full reference in the ERES2 book, estimates that a Cortex M3 processor running at 100 MHz will calculate a CRC check for memory at a rate of around 1 megabyte per second. As modern designs may be slightly more powerful than this, but they may also have more memory, it can take a significant amount of time to calculate the CRC. So in many cases, if you're going to use a golden signature or use CRCs in your system for other purposes, it's useful to have hardware support for CRC calculations. During power-on self-tests, we would usually check all of the processor software. Because of the time taken, even with hardware support, our built-in self-tests will usually be carried out in stages, with only part of the processor software checked at a time. Please note that we'll discuss BISTs in general in detail in the next video. So because of the time taken to calculate the golden signatures, only part of the processor software will be checked at a time during our periodic runtime checks. We'll therefore usually store multiple memory signatures for different areas of flash memory rather than a single signature covering the whole area. So we'll split the memory into blocks, calculate a signature for each of those blocks, store multiple signatures, and then we only need to check part of the memory each time we do a periodic test, and check that part of the memory against the signature that's been stored for that part of the memory. So as we discussed, once we've checked that the processor software is correct, we need to check that we're running the correct processor software. Here's an example of the problems that can arise if we get this wrong. In May 2015, an Airbus A400M cargo plane crashed on a basic test flight less than 5 kilometers from Seville Airport. There were 6 people on board on this routine test flight. 4 were killed and 2 were seriously injured. It was noted after the crash that incorrectly installed engine control software had been the cause. This was essentially appeared to come down to a problem in which the software for the wrong engines was installed during the final phases of the development of this aircraft, and what should have been a very routine initial test flight had fatal consequences. So how do we determine that we are running the correct processor software on a particular system? Company policy may require that each product has a different hardware ID and that this ID can be read by software. For example, suppose the product uses a single microcontroller. We might choose to allocate port 0 or whatever on this microcontroller to record the hardware ID. We can record the ID using, for example, 0 ohm resistors and or say 10k pull-up resistors connected to the port pins. At startup, the software would be required to check that the hardware ID for the board matched the expected value. We would refer to this as a port ID mechanism. So we might have 32 pins on a port, and they could be pulled high or low using appropriate resistors or of appropriate value, and then we've got a digital code, a 32-bit digital code that we can use to identify each particular product. As an alternative, there are various low-cost EEPROM packages that can serve a similar purpose to a hardwired port ID, such as a Maxim DS28E07. This is simply one example. I have no connections to Maxim. Another solution, which is not mutually exclusive, is to incorporate a warrantor unit in the platform. Such a component can be used to confirm that the software executing on the main processor is operating as expected. We'll discuss this further in video 20. So use of a port ID, a serial EEPROM or a similar mechanism cannot guarantee that the correct code is loaded. The code that we load may simply omit the ID checks. For example, it may not check the port ID or it may not access the serial EEPROM. Company coding guidelines and code reviews are therefore usually needed in order to ensure that the port ID or equivalent check is implemented correctly. Please refer to the ERES2 book, Appendix 12, for some further discussions about this matter. We also need to think about security issues in many modern designs. For example, in some parts of the world, chipping of passenger cars has become an issue. This involves changing the system configuration in the main vehicle ECU, usually in an attempt to improve the car performance. As a result, the vehicle may become unreliable or even dangerous. Most car manufacturers would wish to detect if such changes have been made to one of their vehicles. In other designs, we may need to consider the possibility that attempts might be made to make deliberate changes to the configuration of, say, a military system during or before the system use. It's clearly important that we can detect any such tampering. Where security is a concern, we may wish to use physically separate memory areas for storage of the golden signatures and the rest of the processor software. Some of the monitoring techniques presented in later videos in Part 4 may also help. That brings us to the end of this video. Before you continue with the course, please read Chapter 15 in the ERES2 book. Thank you for watching.